Can you hear me? Okay. So I'm going to start by paraphrasing Mike Jordan yesterday. I'm not Paul Hand, I'm not Vlad Voroninski, and by elimination, you have no idea who I am. My name is Ashwin Pananjadi, but today, this is not my paper. I'm going to be super high level. And if you have very deep questions, then there's no poster, so you'll have to contact the authors. So I'm going to be talking today about global guarantees for enforcing deep generative priors by empirical risk. So I think there's a bunch of interesting things here, perhaps some of them new to this community. So again, there may be something nice about going slow. Paul Hand is currently teaching a bunch of underprivileged children in Texas, so he couldn't be here. And Vlad Voroninski runs a company, so he couldn't be here. Okay, so today we're going to be talking about compressive sensing. So in particular, what's compressive sensing? It's about exploiting structure in natural images. We basically think of these things as measurements. These measurements basically correspond to the amount of time patients spend in MRI machines, for instance, in medical imaging. So the fewer the measurements, the better we're doing. And how can we take fewer measurements? We have to exploit natural structure. So the signal on the right has way more structure than the signal on the left. Classically, notions of structure are band limits, sparsity, but typically with respect to fixed bases. So these are bases that are hand designed, the wavelets, the frequency domains. There's also a set of things you can do with model-based compressive sensing, but again, usually fixed bases. But this talk is going to be about images that can be represented in the range of a known neural network. So hopefully, using a neural network to model these images lowers our bias in the modeling. So just to make that pictorial, what are we going to do? We're going to do compressive sensing. So we're going to take random Gaussian measurements of an image here. But the image is going to be assumed to come from the range of a known neural network. So here is a neural network. There's a very small dimensional code that basically generates this image. And we'd like to be able to exploit this structure to then recover the latent code. So this is very similar to traditional compressive sensing. You should basically think of this as analogous to a sparse vector, the wavelet basis, and then some compression. So that's going to be the setting we'll study. So why is this a nice thing to study? Why are people suddenly interested in all of this all of a sudden? Well, there was a paper last year, basically, from a bunch of folks in Austin that showed that for many data sets, if you take this deep generative prior approach, you're doing way better than if you just took a fixed basis sparsity approach. So in particular, if you look at the number of measurements it takes to achieve a particular level of error in the reconstruction, then the methods based on these generative networks allow you to do this with, like a factor 10 fewer measurements for the same error. And that's huge because, if you're using this for medical imaging, that basically, divides your time by 10. Of course, this is not medical imaging, this is MNIST. And similarly with CELAB. So as we do things, this is sort of a proof of concept. But the key takeaway here is precisely the fact that, you get these reductions because you're able to model things better. And this should not be surprising. I mean, neural nets give you this hierarchical capability that fixed bases don't. So what do these people do here? So, well, they set up this loss, and they do gradient descent on this loss. So recall that I basically said that this G, the neural network, is known. So the only unknown here is the underlying code. Everything's differentiable. You can go ahead and do gradient descent on it. And then, like everyone does in neural nets, you pray a little. But the point of this particular talk is to put that on more firm footing. So we'd like to understand why gradient descent could work in a setting like this. Okay. So the setting is going to be very simple. You're going to consider a generator network that takes a latent code in k dimensions. You should think of k as being small, to image space in n dimensions. The generator itself is going to be given by a d-layer neural network, d for depth. W's are the weights. There's ReLU activations. Ni is the width of each layer. And you take m measurements. So that's all the notation there is in this slide. X naught is going to be assumed to be some ground truth, and you have to go back and find X naught. So a couple of quick assumptions. The first is that of expansivity. So we basically say that the layers get bigger as you go deeper. And this makes sense because sort of the inversion has to be a compression process. And then the second, which I suppose is fine in this community, is that the weights and the A is, of course, Gaussian in the general compressive sensing framework, but the W's are also Gaussian. The W's don't have to be independent across layers, they just have to be Gaussian. It's also the biasless setting. Okay, so the setting is clear, so what do we have to do? We basically have to study that squared loss that I set up before, and the way this paper does that is to study the landscape. So if you actually study the population loss, that is the expectation of that empirical thing that I wrote up there, then for the simple case where k equals 2, so there are only 2 underlying variables you want to recover, and in that Gaussian setting I talked about before, for 2 layers, it turns out that the population loss is quite benign. So if you look at that diagram, you're probably thinking, okay, this gradient descent should work here. So in particular, there's a local maximum at 0, there's a minimum at the optimal point, and there's this weird looking saddle at a negative scaling of the optimal point. But it's not super terrible. But this is precisely the picture, it turns out, that's useful to generalize this to the arbitrary setting. So the high-level informal theorem is basically that. The fact that this picture is essentially true for the empirical risk itself with high probability. So in particular, if the depth is greater than or equal to 2, the generator is Gaussian and expansive, the same assumptions I said before. The number of measurements here is linear in the intrinsic dimension, which is k, linear in the depth, and logarithmic in everything else. Then with high probability, there is a direction for every single point in the space, such that you can descend along that direction, except for a small neighborhood along the around the optimal point and around that negative scaling that I talked about. And the point 0 is a local maximum. So all of these things that I'm saying here, like the neighborhood and so on, can be made super precise. How large is this neighborhood? All of these depend on the dimension of the problem and the various parameters. But then the dependencies are far from optimal, but they're polynomial, so they're not things that you should necessarily worry about at first glance. And this is, I also like to point out that it's optimal sample complexity with respect to k, which is really the intrinsic unknown dimension in the problem. The neural network, remember, is known. Okay. And a couple of other things to say, I suppose, are this is not existential by any means. This is well and truly constructive. And the proof is quite neat. I mean, it requires matrix concentration, but there are weird discontinuities because of these ReLUs, and you have to do a little bit of work. Okay, so let me just conclude with a couple of thoughts. These are not my own, these are the authors. So this is the first global theoretical result. It's completely global, there's no, except for these neighborhood things, there's nothing really local about it. And it makes complete sense that you could run gradient descent on this problem and not worry about it. It's completely non-asymptotic. The recovery proof, this thing that I said about W's and A's being Gaussian, is not required. It's completely deterministic. Typical isometry properties hold here. And there's, I believe, another algorithm that they're coming out with that explicitly avoids this issue at the negative optimum. And I think the thing to take away from this is that these generative priors may actually be better priors for images, and in particular, they may reduce the dimensionality by a lot. This k could be way, way, way less than the amount of sparsity you need to model images. And I suppose future work is to extend this to more real models. I'm glad to take any questions you have, but like I said, keep the tough ones for the authors. Thanks.
All right, so there's time for one question while the next author is setting up. So I have one. So in the simulations and images, was this like a neural network with random weights or with learned weights?
These are neural networks with learned weights.
Okay, so but what if they were using like random weights to do decoding? Will it work or not?
Can you say that again?
But if they do the exact same simulation, but replace the learned network by a random network.
So I understand your question. You're basically saying that if you do a random network, it's not going to model anything. So there's really nothing much you're learning, and you're getting essentially no representative capacity. But I think the reason, at least the one Paul told me, blame him, is that I suppose there are a bunch of papers that show that across training, across different ways of training these networks, that essentially the weights can be shown to be marginally Gaussian. So these are still learned weights, but marginally Gaussian. So that's why that's apparently what justifies that assumption.
Okay, good. So let's thank the speaker again for presenting the work. And next is Sasha Rackling presenting joint work with Noah Golovich and Ohad Shamir on